Gnanam paramam dheyam. Knowledge is supreme.
So today I am going to continue. Last lecture I introduced for you ladder operators, raising ladder and lowering ladder operators, right? So today I am going to try and I am going to do more on ladder operators. Using them, how to find expectation values, it becomes much easier. What will be the Heisenberg equation for the ladder operators, or Heisenberg picture, how the evolution of these ladder operators happen, and then to make things close to classical physics, where you know how the harmonic oscillator, if you try to write the position x of t, you write it as a cos omega t plus b sin omega t kind of expression. You need to find the expectation value to also have similar behavior, and that will happen only if we start looking at specific set of states which is called coherent states. Okay. So this is why this coherent states is important. Okay. So this is the theme for today based on using your ladder operators. Okay. So let's just recap what we did in the last lecture. Hamiltonian in terms of ladder operators, right? It is a dagger a plus half multiplied by h cross omega, dimensionally correct. A dagger a is the number operator which is dimensionless, and their eigenstates which are denoted by the ket n. The number operator on the ket n, nothing but a dagger a, and it's an eigenstate with eigenvalue n, and n's are integers. This also we have argued last time. And the corresponding energy of the same state, it's a simultaneous eigenstates of number operator and Hamiltonian, because it's just proportional to it up to a constant. So that is a shift n plus half h cross omega. This is clear. And we also derived that these are not eigenstates of the ladder operators. And the definition of a ladder operator, A is a lowering operator which takes n to n minus 1, and this coefficient has to be strictly square root of n. This also we derived. We wrote d lambda and c lambda, and we tried to fix these coefficients. Similarly, a dagger raises the state. By raises I mean it takes you from the lower energy state to a higher energy state with one step higher with corresponding coefficient which is n plus 1. And recall, we rewrote the position operator in terms of the ladder operators. We wrote momentum operators in terms of the ladder operators. You can now use the earlier slide properties and try to work out a matrix element between two states with integer n and integer m, whether this will be 0 or non-zero. Shall we work it out? It's really a power of these ladder operators helps you to do this very nicely. So let's do that. So we want to work out the matrix element of the x operator between m and n, right? What is x? Apart from the factors, we'll put the factors later. This is proportional to a plus a dagger. Okay. So this is nothing but m a dag a n plus m a dagger. What is this? A on n root n times n minus 1. You have m n minus 1, and a dagger on n root n plus 1 m n plus 1. These are all what? They have to be orthonormal. So, it will be root n delta Kronecker delta plus root n plus 1 Kronecker. Okay. So, this is what you will have apart from the factors. If you want to write the factors, factor will have a root of 2 h cross by m omega times the 1 by 2. Apart from that, you will have this to be the matrix element of the X operator. Similarly, you can work out for the P operator. What is the modification? It will be A minus A dagger, and then the factors will have a 1 over 2i. Okay. So, this will be the matrix element which is written nicely when you write the X operator in terms of the ladder operators. What will be the expectation value of X in, suppose n is equal to m, it is 0, right? If suppose I ask you what is the expectation value, you can blindly say expectation value of X operator is 0, because A will take n to n minus 1, A dagger will take n to n plus 1, the inner product will always be 0. So, here we did not do this explicit calculation of finding the expectation value which you did in the wave function formalism. Without even doing that, we could say that the expectation value is 0, right. So, that is the important, interesting fact, right. If you remember, I had asked you in harmonic oscillator, V of x is V of minus x. So, if you want to find expectation value of x, it should satisfy that property x expectation is same as minus x, right, and this implies expectation value is 0, right. And now we do it by the oscillator number eigenstates, and we see that explicitly it is happening, and you can write psi n of x as x with n, and you can find expectation value of x, right. You could try to rewrite it in terms of psi n star can do this, can rewrite this as n x x operator x n dx, to give you an eigenvalue, and then, or you can even remove, right, then you can do this, okay. Can even put it as n x operator x x n dx, and then this becomes explicitly, which is nothing but, I have used this identity completeness, okay. So, you can do various things by writing things in a operator fashion. In fact, this in the position space you do not need to put it as operator, but you can try to write it as an operator on x and remove the unit operator and get. So, we went through this in general for any operators. I am just trying to say that how powerful is the ladder operator that you can directly get many of these expectations. What is the next one we could do? Uncertainties. What is uncertainty in x? Delta x is expectation value of x squared minus expectation value of x under square root. So, in the number state n x operator n is 0, What is n? X operator squared on n. So rewrite this as x squared is proportional to a plus a dagger the whole squared. I am not writing those constants, we will put it later. What is this? A squared plus a dagger squared plus a dagger plus a dagger a. Don't write it as 2a dagger. A dagger plus a dagger a. What is the matrix element of a squared? What will be the matrix element of a squared? Somebody? A will reduce it, it's a lowering operator, to n minus 1. Another A will reduce it to n minus 2. And then the matrix element of n and n minus 2 is always 0. This is going to be 0. In fact, matrix element of any power of ladder operator, some number, let me put it as, this is always 0. You agree? The reason is that it is going to lower the state, and when you take the inner product, their orthogonal states, it's going to be 0. Is everybody with me? So the first term expectation value is 0. Second term expectation value is 0. So the non-zero contribution can come only from if you have equal number of raising and lowering operators. That's the first thing you should do. If you have equal number of raising and lowering operators, you get back to the same point. You raise n number of steps, lower n number of steps, you get back to the same point. Then the matrix element will be non-zero. Work out what is expectation value of x squared, which is nothing but expectation value of a dagger plus a dagger a, up to the constants. A dagger on n is n plus 1, n plus 1, correct? Is it right? And n, a dagger a on n will be, a will take square root n, a dagger will give you, it's already reduced to n minus 1. That will give you a dagger on n minus 1 with the square root n. So this piece is another square root n times n. So expectation value of n x squared n is proportional to, up to those factors, you will have 2n plus 1 times, what is those factors? It is 2h cross by m omega into 1 by 4. Is that right? So this is what you get for the expectation value of x squared. This is also consistent with the fact that for symmetric potential v of x equal to v of minus x, even powers of x squared, even powers of x, matrix elements expectation value has to be non-zero, which is what we find. Odd powers of x, expectation value of x is 0. You can also show expectation value of x cube will be 0. Why? When you take the cube, the number of ladder operators which is raising will not be equal to the number of lowering operators when you take the cube. So only even powers will allow at least some terms to have equal number of raising lowering operators, raising ladder operators and lowering ladder operators. That is why those matrix elements are going to be non-zero. So then you can determine what is the uncertainty. Delta x, in this essentially it is other term is 0, right? Expectation value of x is 0. So this one will be, is that right? Similarly, work out for delta p. Not going to do this for you, please do this. And what do you have to check? Delta x, delta p should be greater than or equal to h cross by 2. So please do this delta p and make sure that you are able to verify this uncertainty relation. So the only thing which is upsetting about this number operator states is that the expectation value of x operator is 0. Similarly, you can show p operator is also 0, which means there won't be any evolution of these matrix elements with time, right? And you don't expect it also. Why? Because these are all stationary states. That whenever you want to look at transition and oscillations, you can't do it by living in the stationary state. If you want to look for oscillations, want to see your classical oscillations, you need to be in a superposed state. I said this, right? Some point. You have to be in a superposed states of a number of states or 2 states. Then only you start seeing that the expectation value as a function of time is cos omega t times something plus sin omega t times something. If the state psi is a superposition, if psi was only a particular eigenstate, then this x of t is also 0. If you want to go and look close to classical physics, harmonic oscillator, when you write the position, solution for the position or momentum which is evolving in time, it should have this oscillation cos omega t and sin omega t. You cannot get it with the stationary states. Okay, so let me just summarize here that if you want to determine these matrix elements, which you have already done, we have verified the first equation. This will be on the Moodle. You can verify the second equation and check whether what I have written here is correct. Okay. The operator A, when it acts on 0, it's going to be 0. Sometimes this is little misleading. Why? It appears like a 0 appears like a null vector. Is it a null vector? It's not. Why? The number, the Hamiltonian, when you operate it on 0, it is giving you non-zero energy, plus the state norm of the state is 1. Okay. Even though I write it as 0 and it is the A operator on 0 is 0, this is not a null vector. Don't get confused. Null vector is 1 where any operator operating on a null vector will be 0 and the norm of that vector will be 0. Norm of the 0 is also 1. Okay. So please remember that just because I write a 0 here, you should not interpret it as that it is a null vector. So you can call the 0 as a vacuum state. 0 has the property that 0, 0 is 1. It's the lowest energy state, energy eigenstate, called as ground state or vacuum state. Okay. So this condition clearly tells you that it is not a null state. The lowering operator on the ground state is root n times a lowered state, that root n becomes 0. So you can't lower further below the 0 state, which means there is a lower bound which is 0. You can't go below that. You can only keep going up by the ladder operation. Okay, is the picture clear? Something? You have some parallel processing going on, or is it clear? Okay, so this also we went through, that using this, take the inner product with an x naught on the state and write this to be a first order differential equations now. So the first order differential equation in the position representation for the momentum is del by del x naught h I h cross. So you have this minus I h cross. So this I with the minus I will give you a plus 1. If there is any typo, you should tell me. So what is this? X naught with 0 is the ground state wave function at a position which is x naught, and this is also the ground state wave function. It's not difficult for you to solve this. Solve the first order differential equation and then you make sure that you want to normalize it and get the normalized wave function. See how simple it is. I'm just trying to tell you here, I'm not looking at second order differential equations or anything. I'm just using the power of this ladder operator and I get a first order differential equation from which I find the ground state solution. I'm not invoking any special functions or anything. How do you find the first excited state? First excited state will be, take the ket 1, find its projection on x naught, that will give you the position space wave function of the first excited state at a point x naught. I can write that x naught with 1 as a dagger on 0. A dagger, if I operate it on 0, it is root 1 times 1, which is exactly this, root 1 is just 1. And then what is a dagger? Can write it in terms of x minus ip, substitute them and you get again a first order differential equation. You know psi naught now, you can differentiate and write the psi 1. So it boils down to not knowing any special functions, but you can systematically solve. If you want to find a ket n, what do you have to do? I have to do a dagger to the power of n, but there will be a factor. You have to divide it by root n factorial. So if I want to write ket 1, it is a dagger on 0 divided by square root 1. If I want to write ket 2, it is a dagger divided by square root 2 on 1, which is a dagger divided by square root 2, a dagger divided by square root 1 on 0. I've used this fact that whenever you have to do a dagger on n, it is square root n plus 1 times n plus 1. So I'm just bringing that factor below and writing things. So what does this tell us? You can write any ket n as a dagger to the power of n divided by n factorial or n minus 1 factorial, n factorial on. So if you want to write psi n of x, it is at a specific point x naught, it is this. I can also write it as x naught a dagger to the power of n on 0. Okay, now it will be involving only position and momentum. If you try to write a dagger in terms of that to the power of n, you will have a series, but you have to operate it on the ground state wave, right? You can write this as this is a function of x minus ip. You can write it as a function of x minus I times minus I h cross del by del x naught, some function form, or you can even write it as x naught to the power of n divided by root n factorial on psi of x0. That's it. Is this difficult? You can work it out and find all the excited states. All the excited states can be found from the ground state by doing the A dagger operation, and A dagger involves only these differential operators which has to operate on the functions whose function you know. I am just trying to show that the ladder operators, when I started introducing, it might have looked abstract, but without going into the details or looking at second order differential equations, using the power of operator algebra, I have managed to get the energy eigenfunctions and also the corresponding energy eigenvalues as n plus half h cross only. So this is the tool which is really, very powerful, and it's applicable to many complex systems. We try our best to map it to either a harmonic oscillator algebra. So when I say harmonic oscillator algebra, I know that I can write an A operator and an A dagger operator, and I can solve that problem. Okay. So this is why the power of operators and Dirac formalism is really useful. Okay. So you can continue like this and determine all the other excited state. As a check, you can do the second excited state and see what you get. This we have already worked it out. Expectation value is 0, right? And similarly, expectation value of P will also be 0. What about standard deviations or uncertainties in X and P? For that, you need to work out expectation value of X squared and expectation value of P squared, and this also you could. We did this for the specific state, and you verify that. After you do for P squared, you verify that they satisfy the uncertainty. I'll leave it to you to do this.